Hello out there to you. Let's do some more complicated game theory problems with some payout matrices that are not 2 by 2. So typically we see the 2 by 2 matrices in classes, but every once in a while you might run into, or maybe you're in a hardcore game theory class and you want to think about games that are a little more complex with more strategies. Okay, so a strategy, by the way, is just a choice. So let's go over some game theory vocabulary here real quick. A strategy is a choice. A payoff matrix, that's what you see here. So it's a list of payouts given the two strategies of each player. Each player, typically in a business context, they're going to be companies. This first one is Intel and AMD. And it could be anything. Most of the time we analyze these games where they're choosing simultaneously, meaning at the same time. So that would be a game like, say, baseball, or if you don't have any information about the other player, you have to pick at the same time that the other player has to choose. And then sequentially, it would be a game more like checkers or poker, where one player plays before the other player. Okay. A dominant strategy is a strategy that's better off for either player or for a single player, regardless of what the other player decides. Okay, so you're always better off choosing choosing this option or this strategy if you have a dominant strategy. A dominated strategy, I wish they picked a different term for that because it's really close to dominant strategy. It's a strategy you don't pick. So it's a strategy that basically can be eliminated because under no circumstances would you pick that. Okay, and then finally, a mixed strategy is just a set of strategies where your best decision depends on the decision of the other player. So that'll occur when you don't have a dominant strategy. So here we've got a pricing game. Intel and AMD are both making chips, but they need to choose simultaneously right there. And we need to choose a price. So AMD can choose all of these prices along the top, and Intel can choose these prices here. The way to read this, the first number in the payoff matrix belongs to the left player, and the second number belongs to the top player. Okay, that's the way to read these. Okay, so let's start analyzing this using Intel. So it looks complicated, but it's really just has more strategies. So if AMD chooses 449 as their price, what's the best payout for Intel? Okay, so the best payout for Intel is this one. Okay, this is 230 is the highest payout. Okay, if AMD chooses 399, what's best for Intel? It's that one. If AMD chooses 349, and it's that one. If AMD chooses 299, if AMD chooses 249, okay, and looks like Intel never picked 299 or 249, so we would say that those are dominant. Oh, or 449. We would say that those are dominated strategies. Okay, they've been dominated by all the others. Okay, and then let's do AMD here. Intel could be in that color. Okay. Okay, now if Intel chooses 449, the second number we're going to look at, which one is best for AMD, it's that one. Which one is best for AMD? It's that one. Already we've got a Nash equilibria. Okay, and looks like AMD would never pick 249 or 449, so those are dominated strategies, and those can be eliminated as well. We do have a Nash equilibrium in this game. It is possible to have a game where there is no Nash equilibrium, but this is the Nash equilibrium. Okay. All right, and that's how to solve that one. Okay, let's do a whole bunch more, and I encourage you to stop the video and try it yourself. Okay, so we'll do this player, and then let's use green instead. Okay, so pause the video. I got player 1 and player 2. Pause the video, give it a shot yourself, and then I'll come back with the answers. Okay, hopefully you pause the video. So in this game, we've got this player 30 because that's the most there, assuming that these are the best. Okay, so here I've got a tie. I've got 25 on choice A or B on player X. So they're kind of indifferent when player 2 chooses X. Over here and over here. Okay. So they could pick any of these strategies. No dominated strategies. No dominant strategy either. Just a pure mixed strategy. Okay. If player 1 chooses A, what is the best payout for player 2? It's that one. It's that one. It's that one. And oh, we've got another tie. Now those don't really matter because if player 1 sees that player 2, or sorry, if player 2's outcomes are never going to be Z or X, because when player 1 plays D, they're only going to do that if player 2 has played W. So we do kind of have a Nash equilibrium. Now if they pick at simultaneously, then we're likely to see player 1 pick either A or C, and then player 2 picking X. If they play this game sequentially, okay, then it depends on who goes first. And so you ask yourself, who goes first? And if player 2 has to go first, they're going to pick Z. Okay, and that's because they want player. No, I guess I wouldn't say that. I wouldn't say player 2 would pick Z. Player 2 is going to go after the best outcome that they can get, which would actually be likely Y. Player 2 wants Y because 25 is their highest. Okay, and if player 2 chooses Y, player 1 is going to choose C, and then player 2 would be pretty good about moving to X, which would then give us that sequential equilibrium. Okay, that one's a little complicated. We'd need a little bit more guidance on that one. Okay, all right, let's do this one. We'll call this person player 1, and this person player 2. Pause the video. Okay, hopefully you're back. You gave it a shot. So here are the solutions. Here they're indifferent between here and here, and they're indifferent between here and here. So this game not likely to be asked to played simultaneously. It would be sequential. Player 2, what would be their best outcome here? Ooh. And then they like 0. So simultaneously, this game does not have a solution. It does look like, to me, it's a prisoner's dilemma because we're likely to end up in a outcome right here. So that is a possible equilibria there. So ask yourself this: if it's simultaneous, if player 2 is picking first, what is the best outcome that player 2 can hope for? And that would be to pick A, but that player knows that player 2 knows that if they pick A, player 1 is going to pick B, and that results in that number there. So really the best that player 2 can hope for is either here or here. And so they kind of like option A, I suppose. And then player 1, if player 1 picks first, they're going to pick B. Okay, B is pretty good for player B, or player 1 rather. And given that player 1 plays B, it'd be indifferent here or here, but they definitely wouldn't want to pick A. So we would likely end up with a sequential choice of both players picking B. This is a bad game for player 2. I want to get out of that game. Okay, let's do this one. Okay, And so I've got this player and this player. Okay, so the row player likes this, this, or this. And they like this, this, or this. And they definitely like that one. And then they like that one. Okay. Let's see where they go from here. They like that one. They like that one. Okay. And this game does not have a solution. So we don't have a Nash equilibrium. We could maybe figure out sequentially, but we don't have a simultaneous play equilibrium. All right, let's do this one. You can do as many of these as you want or as few. It's up to you. It's the magic of YouTube. Okay, so let's do player 1, player 2. Okay, so there. Just circling the best given the other player. What kind of animal will we build? I don't know. Well, we don't have Nash equilibrium there, so no outcome that we can bank on there. How many more do I have? I have just a couple more here. Okay, let's do this one here. Pause the video. Okay, we'll call this player red, this player blue. Okay, red player. Red player has a dominated strategy, and it looks like we do have a Nash equilibrium. We do. So this game does have a simultaneous play. So there's your Nash right there. Okay, this is another one I'm looking at. It's needs to be thought of sequentially, so we'll skip that one. You can do it if you want on your own. Okay, this looks like a good one, and it's good because it's written in the, it's got these dashes here, so we'll do the blue player first. Pause the video. Hopefully you're back. Okay, here. What's the red player going to do? Red player is going to do this, this. This game does not have a Nash equilibrium. No solution there. No dominant strategies. Okay, looks like the last one. 3 strategies each. Here's the payoff matrix. Okay. Pause the video. Okay. Player 1. Okay, player 1 is never going to pick top. That strategy is dominated. Player 2. Hey, we got a Nash equilibrium. We also have a prisoner's dilemma because this outcome is worse than this outcome up here. If they both colluded, they could get to that outcome there, but it's not likely to happen because the payoff of cheating on that collusive agreement is pretty high, so we're not likely to see that. But that's how to solve some more complicated game theory payoff matrix.